All right, how are we doing? Now, I won't be able to hear you, but there is the chat that's available to you. So if you've got questions, please feel free to voice them there. Can everyone hear me well? How are we doing? Today we're going to talk about, thank you. We're going to talk about some work that I was, some stuff I was doing in the summer. Namely, I was trying to see the connection between these two series, right? First of all, let's recall we introduced the sigma notation last week. So you know what this means, right? This is 1 over 1 squared, or just 1, plus 1 over 2 squared, plus 1 over 3 squared, and so on. And we suggested that this converges to pi squared over 6. Now, it's a well-known result, a bit beyond our means, but nonetheless, something that's very well known. Similarly, the series 1 over n to the 4, which is 1 plus 1 over 2 to the 4, plus 1 over 3 to the 4, and so on, is equal to pi to the 4 over 90. So what I was wondering, these kind of look similar. Is there a relationship between the two series? Of course, if you square every term in this series, you get this one. That's an obvious relationship, but there's no way to do that. If you square the whole thing, you're going to get these things squared, but you're also going to get some non-square terms. Terms that are no good, terms that don't appear here. So you don't really want to do that. Really, the question I was asking myself is, if you have the series 1 over n squared, can I multiply this by some other series to give me the series 1 over n to the 4? That's the question I was asking. And if so, then what are properties of this new series? So my approach was the following. A nice result of Euler. So let's consider what he did, and maybe we'll build on that. Euler starts with the series 1 over n. We've seen this series, right? This is 1 plus 1/2 plus 1/3, and so on. Not only did we see that series, but we also saw that it diverges. So that sum is infinity. What Euler does is he says, well, look, you're adding over the natural numbers. And we have the fundamental theorem of arithmetic, which says that every natural number can be decomposed into a unique product of primes. So what if I took all those primes, all those powers of primes? Right? So, let's call the primes P1, P2. Well, let me call them P, Q, R, and so on. Right? So here, look at the smallest prime and multiply that by the next smallest prime, 1 over Q squared, and so on, and 1 over R and 1 over R squared. where P, Q, R are all the primes there are, right? So, I mean, of course, you know the first prime is 2. So this is really 1 plus 1 over 2, 1 over 2 squared, 1 over 2 cubed. And then the next prime is 3, so 1 over 3, 1 over 3 squared. And then the next prime is 5, so 1 over 5, 1 over 5 squared. And so on and so on. His observation was that every natural number is a product, a unique product of primes. So if I have all the powers of each prime, then I can build any number I want, right? So if you're looking at 1 over 12, which comes a bit later in this sum here, 12 is 2 squared times 3. So 1 over 12 is going to be part of this product, right? I'm going to take the 1 over 2 squared. I'm going to take the 1 over 3. So this times this, and then times 1 in each of the other terms. So you see that this sum is now this infinite product. How you doing? So this sum is this infinite product of infinite sums. But if you look closely, each infinite sum in the brackets is really a geometric series. So you can work out the sum of each of the things in the brackets. This is a convergent geometric series, and you know what it converges to. What does it converge to? This one here converges to geometric series from last week, to 2. Indeed, to 2. Let's rewrite it as 1 over 1 minus 1 half. But it is 2, right? 1 over 1 minus a. And the second one, same thing, 1 over 1 minus a third. And the next one, 1 over 1 minus a fifth. And so on and so on. Or, if we view them just as P, Q, R, and so on, because it's over all the primes, 1 over 1 minus 1 over P, 1 over 1 minus 1 over Q, and so on and so on. But that is really P over P minus 1. And that is Q over Q minus 1, and R over R minus 1, and so on and so on. So it's this product of primes. And now his observation was, well, you have an infinite product of primes. Well, no, I mean, his observation was, if you only have finitely many primes, you're going to have a finite product here, which is not going to be infinity. So the only way you can have infinity is if you had an infinite product of primes. So that was his argument, right? So another proof of the infinite number of primes. What I wanted to do was apply this argument to the series 1 over n to the 4. So let's do it together. Let's apply this to the series 1 over n to the 4. Right, and split, so the same idea, right? Because every natural number is going to be a product of primes. So we're going to do exactly the same thing and view this as a product, right? 1 plus 1 over p to the 4 and 1 over p to the 8 and so on. And same for the other prime. So we're going to view it as a product of each of these things. In the same way that every natural number was a product of primes, I mean, you're doing the same thing, but just to the n to the 4. So this, again, geometric series with 1 over p to the 4. So this converges to 1 over 1 minus 1 over p to the 4. And this one converges to 1 over 1 minus 1 over q to the 4. And so on and so on. So it's this infinite product. Or if you rearrange that properly, this is p to the 4 over p to the 4 minus 1. And q to the 4 over q to the 4 minus 1, and so on. So it's this infinite product of these prime factors. But this factors nicely. This factors as p squared over p squared minus 1 times p squared over p squared plus 1. And same thing with that. So if you group the stuff in p minus 1s, right? If you group the stuff, let's group these together. You get p squared over p squared minus 1, q squared over q squared minus 1, and so on. And then the other ones, p squared over p squared plus 1, q squared over q squared plus 1, and so on and so on. But these are really 1 over, if you work backwards, instead of to the 4, it's now just squared. So this is really 1 over 1 minus 1 over p squared, 1 over 1 minus 1 over q squared, and so on. And do the same thing here. This is 1 over 1 plus 1 over p squared, 1 over 1 plus 1 over q squared, and so on and so on. But these, again, we're just working backwards. This is just the geometric series. 1 plus 1 over p squared, 1 over p to the 4, 1 over p to the 6, and so on. Same thing here. 1 plus 1 over q squared, 1 over q to the 4, and so on. And these ones, well, now you've got the plus, which is not really what you were expecting. But, of course, there's a simple way around that. Plus is minus minus. So this business, where you're multiplying 1 over p squared, in the same way, is just the sum of 1 over n squared. So you see, it's this series, or the series corresponding to these things, that will give us what we want. So what is that? Well, this is 1 minus 1 over p squared plus 1 over p to the 4 minus 1 over p to the 6, and so on and so on. Right? So it's an alternating, because it's really powers of minus 1 over p squared. And same thing here, right? 1 minus 1 over q squared plus 1 over q to the 4 minus 1 over q to the 6, and so on and so on. So what we want to do is rewrite this in some nice closed form. And so what is that? Well, so now let's think about what's going to happen. You're going to multiply these things out. Think of foiling all of that stuff. And what's going to happen? You're either going to get a plus or a minus. So a negative 1 to something. And then you're going to get denominators that are something squared. So it's going to be 1 over n squared. And then you've got some power here that you're not really sure about. So the question is, what is that something? And let's illustrate really with an example. So really the question is, what is that something? What is this? Let's backtrack and try to come up with it, right? So the first prime is 2. So you're really looking at 1 minus 1 over 2 squared plus 1 over 2 to the 4 minus 1 over 2 to the 6, and so on. The next prime is 1 over 3. Next prime is 3, so minus 1 over 3 squared plus 1 over 3 to the 4 minus 1 over 3 to the 6, and so on. And then the next one would be 5, so 1 minus 1 over 5 squared. And then you know, let's multiply some stuff out, right? I mean, 1 times 1 times 1, we always have the 1. The 1's always there. And then we're going to get a minus 1 over 2 squared by multiplying this with 1's all the way through. And then the next smallest number is going to be 1 over 3 squared, which you get by multiplying 1 with that and 1's all the way through. So minus 1 over 3 squared. And then the next smallest term is going to be 1 over 4 squared, or 1 over 2 to the 4, which is going to be positive, right? You get it by multiplying this with all the 1's. So 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared is here, which you get by multiplying this with 1s. So you get a minus 1 over 5 squared. And then the 1 over 6 squared you get by multiplying these two. So this times that, and then all 1s. So minus minus gives you a plus, and so on and so on. So, right, I mean, this is our sum that has the form negative 1 to the something times 1 over n squared. The only question is, what is that something? How do we make sense of that? 4 squared, yes. 4 squared, but it's really 2 to the 4. So, I mean, they're equivalent. Absolutely. Right, and then the 7, since 7 is prime, is going to be a minus 1 over 7 squared. And so on and so on. Let me just point out that the 8 squared is 2 to the 6. Right, so minus 1 over 8 squared. Might as well talk about the 9 squared, which is 3 to the 4. All right, anyway. So let's stop, but that's the point. So the question is, what is this thing? How do I make sure that corresponding to 2, this should be an odd number. Corresponding to 3, it should also be an odd number. But corresponding to 4, it should be an even number, right? Because negative 1 to an odd number is going to give you negative 1, and negative 1 to an even gives you positive 1. So corresponding to 4, you want it to be even. Corresponding to 5 should be odd. Corresponding to 6 should be even. 7 should be odd. 8 should be odd as well. But 9 should be even. So what is that something? Turns out there is a function that spits back exactly those things. It's known as the prime omega function. Well, the big prime omega function, the capital Omega function, phi of n gives you the number of prime factors of n, distinct or otherwise. Right, so phi n, let's say phi n, but it's written here, it's omega n. Omega n gives you the number of prime factors of n, distinct or otherwise. So phi of 2 Well, 2 is prime, so there's only one factor, 2. Phi of 2 is 1. Phi of 3, 3 is prime. It only has the one factor. Phi of 3 is 1. 4, which is 2 squared, or 2 times 2, right? It has 2 prime factors, 2 and 2, distinct or otherwise, so they don't have to be different. 2 factors. Phi of 4 is 2. I keep saying phi, it's omega. Omega of 4 is 2. Omega of 5, you tell me. How many prime factors does 5 have? Just the one. What about omega of 6? How many prime factors does 6 have? It has 2 prime factors, 2 and 3. Omega of 12, which is 2 squared times 3. What is omega of 12? Omega of 12 is 3. Exactly that. Right? 2 times 2 times 3. 3 prime factors. Omega of 12 is 3. So that's what we're looking at. This function, this series, this is the series such that when you multiply it to 1 over n squared, you get 1 over n to the 4. So the series 1 over n squared times the series minus 1 to the omega n 1 over n squared gives you the series 1 over n to the 4. But since this is pi over 6, and that one is, this one is pi squared over 6. This one is pi to the 4 over 90. By dividing, you see that this series must converge to pi squared over 15. Isn't that interesting? Now, observe one of the exercises I gave you. You know, we were given this, and one of the questions was, what about if we just added the odds? Right? I mean, this is 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, 1 over 5 squared, and so on. What if you just added the odds together? Series is different, might converge to something different. Can we figure out what it converges to? And the trick is to not add the odd ones, but rather add the evens. And what does an even number look like? An even number has the form 2 to the n. 2n rather. An even number has the form 2n. So if you look at the sum of the evens instead of the odds, right, this is 1 over 2 squared when n is 1, plus 1 over 4 squared, plus 1 over 6 squared. But this is really sorry, it's a bit dusty here. This is really 1 over 4n squared. And if you factor out the 4, we know that this series converges to pi squared over 6. So the evens will converge to a quarter of that, or pi squared over 24. And consequently, the odds, and how do we represent an odd number? What do odd numbers all look like? Even numbers, 2n. Odd numbers, 2n plus 1. Exactly. So if you add the evens, and the odds, you get everything. But this is pi squared over 6. This we just worked out to be pi squared over 24. So this one is the difference between the two. It's the difference between the two, pi squared over 6 minus pi squared over 24, which is, this is 4 minus 1 is 3, pi squared over 24, or pi squared over 8. Thank you. Right, so this is the idea I had in your assignment, in the exercises I posted on my courses. This is a well-known idea that we're going to apply to this function, to this new series, whose sum we have just discovered. Right, so we're going to apply that. Apply this trick to that series. Let's apply that trick to that series, see if we can get anywhere. So we investigate what happens if instead of looking at n, we look at the evens. What happens? So we have phi 2n, 1 over 2n squared. Can we work this out? Well, the 1 over 2n squared, the same trick is going to work, right? You square that, and you get 4n squared, and you factor out the 4. So we're well on our way. It's going to be 1 over 4 The only issue, what is phi of 2n? And we don't have much experience. I have so very little experience that I keep referring to it as phi when it's really omega. What is omega of 2n? Well, omega counts how many prime factors you have. So how many prime, right? There it is. Omega counts how many prime factors you have. So here you're going to have an extra 2. You're going to have an extra 2. So phi of 2n is going to be however many prime factors n had plus 1, namely the 2. So it's going to be 1 plus omega n. A very nice observation. So this is -1 to the 1 plus omega n, 1 over n squared. And then take a -1 outside, because -1 to the 1 plus that is -1 to the 1 times -1 to the omega n. So take a -1 outside, -1 over 4, -1 to the omega n, 1 over n squared. And this, this is just, this is just pi squared over 15. So the whole thing is negative pi squared over 60. If you're summing over the evens, you get negative pi squared over 60. But of course, the whole sum is the sum over the evens plus the sum over the odds. And so the sum over the odds in the same way as it was before is the difference between the two, right? The evens plus the odds gives you everything. So the odds is everything minus the evens. So that is 4 plus 1 is 5. 5 pi squared over 60, or pi squared over 12. So if you're summing over the odds, pi squared over 12. How are we doing? Questions here? All right. Well, so that's nice. So before I erase this, so the sum over the odds, pi squared over 12, sum over the evens, is negative pi squared over 60. The sum over everything was pi squared over 15. The original sum we were trying to find, I mean, we worked this out. So that's our original, that was our original observation. And then from that, we applied the trick for the 1 over the even squared, and it turned out to give us some results there. But now let's look at this. Pi squared over 12. What is happening here? Pi squared over 12 versus the original sum of 1 over n squared, which was pi squared over 6. Well, isn't that interesting? Two of these will give you that. So pi squared over 6 is 2 times pi squared over 12. And pi squared over 12 is this. It's the sum over the odds. All right, well, so what's happening? What are we going to do? Right, I mean, here you have all the numbers. Here you just have the odds. Some of them are going to be negative. Some of them are going to be positive. So let's break this up into the positives and negatives. Right, so we have the sum overall is twice the sum. Here I'm just rewriting this equals that. And I'm going to decompose this further into the terms for which phi of 2n plus 1 is even. Plus the terms over which phi of 2n plus 1 is odd. Now, if phi of 2n plus 1 is even, this is going to be even, and negative 1 to an even number is negative 1. It is positive 1. So I don't need this. And if phi of 2n plus 1 is odd, this is an odd number. -1 to an odd number is just -1. Yes, I'll. This will be recorded. I'll post it on. Yeah. So let's say minus phi 2n plus 1 is odd. 1 over 2n plus 1. All right. So what do I want to do here? Let me call this E, because we get lost in the notation and we just becomes messy. Let me call this E. And let me call this O. So E minus O. E minus O is actually what, right? I mean, it's 2. So this is pi squared over 6. So E minus O is actually pi squared over 12. Exactly the result we had right here. So E minus O is pi squared over 12. And E plus O, right? Instead of subtracting the two, if you added them, this plus that, well, this is the sum of the evens. This is the sum when phi of 2n plus 1 is even, and this is the sum when phi 2n plus 1 is odd. So odd and even gives you everything. So this gives you the sum over the odds squared, which I've conveniently erased it, but it's pi squared over 8. So now you have two equations, two unknowns, and you can actually solve for each of these. I'll let you work those out. I mean, if you add the two, why don't we do it? If you add the two, E plus E is 2E, minus O plus O is 0, and this plus this. So what is that? 48 is the smallest common denominator. Is that right? Probably not. 24. So 2 plus 3, that's 5. 5 pi squared over 24. So E is 5 pi squared over 48. And then the difference, well, whatever. Something easy to see here. It's going to be 5 minus 4. So that's pi squared over 48. Is that right? When you add the two, you get 6 over 48, which is pi squared over 8. And when you subtract the two, you get 4, which is pi squared over 12. There it is. All right, so there it is. That's what I have so far. And where am I going with this? Well, I mean, so first of all, you have these nice results. I only did it for 1 over n to the 4, but I mean, it generalizes immediately. I'm sure you see that. Second question that arises, because here's a nice question. We know what the series 1 over n squared converges to. But what if, instead of taking all the numbers, you just took the primes? Right, so 1 over 2 squared, 1 over 3 squared, 1 over 5 squared, 1 over 7 squared, and so on and so on. Nobody knows what that converges to. And I feel that we're very close to that. Because you see, they're all included in here. Right? Because phi of p is 1, so that's odd. So they're all included in here. Here you have some extra stuff. Right? So in here you have all the primes squared. You also have some extra stuff, like the primes cubed squared, and products of 3 primes and products of 5 primes and so on. Can you subtract those? Can you take those away from this? So that's where we are. Very close. And you know, I feel, I mean, I haven't had much time to work on this since the summer, since classes have started, but you know, I feel we're pretty close here. So that's where you come in. You got to work on that tonight, tomorrow. See what happens. Can you remove the bad stuff? Questions? Because, you know, coming up with this as some fraction of powers of pi squared, that would be amazing. It would be an amazing result. If you search online for the sum of the reciprocals of prime squared, there's almost nothing. It'll tell you that this is 0.54 something something. It's an approximation. And that's really almost all we know. The midterm will certainly cover everything we've done so far, maybe more. Details to come after the break. And there is no class on Thursday. Questions? Anybody? How are we doing with this stuff? Right, so try to work that out. What can we do here? How would I recommend to study for the midterm? Reread your notes. Make sure that the material you're comfortable with. I've posted exercises on my courses. There's a whole module for exercises of each topic we've done so far with solutions. So I mean, that's what you should be doing. Those exercises. Make sure you're comfortable with those. The midterm might be similar to that. Questions? Right now, I'm thinking that the midterm will have a multiple choice portion and a long answer show your work portion. So of course for the multiple choice, you don't have to do anything. So are we expected to provide proofs for all formulas on midterm? If it's just asking you, I mean, unless it's asking you to prove, then you can use a formula. In particular, if I'm thinking geometric series, if I gave you a geometric series to evaluate, you could just use the formula. Although I could ask you to prove that the geometric series converges, and then that's where you do the trick with the telescoping sum business. Questions? Anybody? No? Seems like a good place to end then. Thank you all for coming. Hopefully, well, I mean, I was going to say, hopefully things come back to normal very soon, but I mean, it's not going to be an issue for us. I'm sure things will be resolved certainly by the end of Thanksgiving holiday. So you guys have a good holiday, and I'll see you when we return. Thank you for coming, and have a good one. Anybody have any questions? Is Elisa there? No, maybe she didn't. It's all good then. Very well. So you guys have a good one, and I will see you after Thanksgiving break. I don't have any office hours today, and then Thursday. If we're back on campus, I should be there Thursday afternoon. Yeah, so office hours, normally it's Tuesday, Thursday, 3 to 5, 3 to 5:30, just before class. Yeah, so try me on Thursday if you've got questions. For web work, it's well, I mean, it's probably best to come to office hours. But I mean, if you've got a quick question, we can do it now. It's no problem. Do we have a quick question? No? I'll wait for another minute. I know there's a lag here. Has anything been announced as far as back to school is concerned? Anybody know of anything? Square root of the complex numbers? Yes, yes. What is the issue? You know what to do, right? You know what to do. You wish to express this in the form a plus ib. Right? You want to express this in the form a plus ib, so you square both sides. Well, I was splitting up right here. Okay. So here if you square both sides, square this, I'm sure you know what it is. It's a squared minus b squared plus I to ab. And then you equate real and imaginary parts. Real part here, real part there. Imaginary part here, imaginary part there. And then whatever you want to do, maybe solve for b. Right? I mean, the point is you have two equations, two unknowns. So hopefully we're able to solve. When you solve for b, b is 1 over 2a. Plug that into here. So you get 2 is equal to a squared minus b, which is 1 over 2a. Or 2 is equal to a squared minus 1 over 4a squared. Multiply both sides by 4a squared so that you get rid of the denominator. So you get 8a squared is equal to 4a to the 4 minus 1. Bring this to the other side. And what you realize is that you have a quadratic. I mean, it looks like a polynomial of degree 4, and it is. But it's actually a quadratic in a squared. If you let x be a squared, this becomes 4x squared minus 8x minus 1. Quadratic in x. So you can apply the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, so plus 16 over 2a. So 64 plus 16 is 80. So that's 8 plus or minus square root of 80 over 8. Well, whatever. This is very close to 81, right? So it's very close to 9. And 8 minus 9 would be a negative number. Remembering that x, which is a squared, right? You don't want, since a must be a real number, you don't want a squared to be negative, so you have to take the positive. So a squared is 8 plus root 80. And so a is the square root of that. And then you get your b using this. And you're set. You're all set. Hope this clears things up. Questions? Anybody? Anyone else? Aliza, are you there? No? All right. Well, thanks again for coming. And I will see you guys after the break. You guys have a good one. I'll post this on Will the Final Exam Be Open Book. It's a online final, right? So you're allowed to use the full power of the internet. Of course, the work you submit should be your own. So don't full power of the internet minus those online forums where you can ask questions. And so, yeah, so that, I mean, look, you can do the research, but the work you submit should be your own. Don't have somebody else do the work for you. All right. Thank you, folks. You guys have a good one. I'll see you in 2 weeks.